how this can be applied, you refer to the non-homogeneous differential equation. an yn plus an minus 1 yn minus 1 until a1 dy dx plus a naught y equals to gx. The gx is called the non-homogeneous part. So the general solution, as you know, we already solved for the complementary part. This one comes from the homogeneous part. And the yp is the issue now. The yp is for the non-homogeneous part. Non-homogeneous part. So end of the day, your y must be equal to yc plus yp. So the variation of parameter method consists of two parts. First, you must solve the associated homogeneous differential equation. You see the right hand side. It can be a constant coefficient or it can be Euler, Cauchy-Euler, because we study two types, Cauchy-Euler and then constant coefficient. So you already know how to find yc. So the yp, you already done undetermined coefficient method. But today we are going to do for the variation of parameter method. So the variation of parameters method is to tackle the gx. But the problem with gx is it can take various form. So we will see for which function the variation of parameter method is suitable when you look into this gx. So the particular solution for the non-homogeneous part which you want to find, first you have to create this. For the second order, you have yp. This is y subscript p is the particular solution equals to u1x multiply y1x plus u2x multiplied by y2x. So u1, u2, this one we will find later. But y1, y2 obtained from the solution of homogeneous equation. So this yp include y1, y2. And then u1, u2 we will find later by using the variation of parameter method. So the variation of parameter method is to find u1 and u2. And y1, y2 you already obtained from solving the homogeneous differential equation. So now the method of solution variation of parameters involve two parts. One is first you have to find complementary solution. Complementary solution is the y1 and y2. In order to find complementary solution, you have to solve the homogeneous differential equation. This is homogeneous differential equation. It can be constant coefficient or Cauchy-Euler. A2 y double dash plus a1 y dash plus a naught y equals 0. So you create this yc. You know already that yc is c1 y1 plus c2 y2. What we need is we take out this y1 y2. We take out and then we put it in variation of parameters method. Now you will see later where you want to plug in the y1, y2. Now the step 2, normally you have the general form, this one. A2 y double dash plus a1 y dash plus a naught y equals gx. It can be constant coefficient or it can be Euler, Cauchy-Euler. But you must write in standard form. This one very important. Standard form meaning 1 y double dash plus px y dash plus qxy equals to fx. This is called standard form. 1 y double dash plus px y dash plus qxy equals to fx. And then step 3, you compute the u dash 1, u dash subscript 1, u1. This one already defined w1 divided by w. So w1 is defined like this. Matrix 2 by 2 matrix. First row 0 y2. You already have y2. Second row fx y2 dash. You already have fx from here. You plug inside here. Y dash subscript 2, you differentiate y2, you get y2 dash. This is w1. Divided by w. W is the matrix 2 by 2. You create by putting y1, y2, row 1, row 2, y1 dash, y2 dash. So this is to calculate u1 dash, w1 divided by w. You see w1, 0 multiply y2 dash 0 minus y2 fx. This is what you get. Divide by w, w comes from here. Now u2 dash is w2 divided by w. But w2, you get it from here. This matrix using algebra, 2 by 2, determinant. First row, y1, 0. Second row, you differentiate y1 dash. And then here you put fx. Second row, second column, this is fx. So if you take determinant, y1 fx minus y1 dash 0, you get y1 fx divided by w. So you know the right hand side. Later on, we will integrate to calculate the u2 dash. Now, how to calculate u1? You integrate u1 dash because this is du1 dx. du1 dx, you integrate, then you find u1. This is du2 dx. So you integrate, you can find u2. So final particular solution, you take u1, you put it here, and then u2, you put it here. y1, y2, you already knew. So you can create your yp. So after that, you substitute for general solution, you have yc, and then yp, this whole thing, you put it here. So we already successfully solved the problem with variation of parameters method, which involve 6 steps. Remember, yeah, altogether we have 6 steps. So the 6 steps you can simplify. You no need to do all the steps. You can cut short, make it easier. Any question, class, so far? Before we move on to the examples, any questions? Any questions? Okay, so we move on to example. Yeah, sometimes it's very hard to understand the methods or the steps and the workings without examples. So if you look at the example, from example, you can understand much more better, and then try to match with the steps. So we want to solve this second order linear ordinary differential equation, y double dash minus y dash minus 4y dash plus 4y equals to e2x divided by 1 plus x squared. The problem with this differential equation is this right hand side. This function, you cannot use undetermined coefficient method to solve this. The reason is there is no way you can create the yp from this, because it's not e to e power 2x. It is e to the power 2x divided by 1 plus x squared. That is the difficulty. So in that case, the best method at the moment is variation of parameters. So first, step 1, you must find complementary solution. So complementary solution, you solve the homogeneous equation. Y double dash minus 4y dash plus 4y equals 0. This is homogeneous equation. You create auxiliary equation, m squared minus 4m plus 4 equals to 0. So this is your, what we call your auxiliary equation. So you try to factorize m squared minus 4m plus 4 equals 0 by using factorization or any quadratic formula. In this case, if you factorize, this one easy to factorize, m minus 2 multiply m minus 2 equals to 0. So your m1 equals to 2, your m2 equals to 2. These are two equal roots. So the complementary solution, yc, c1 e to the power m1x plus c2 x e to the power m1x. Because these are repeated solution, so you put x inside here. So your yc becomes c1 e to the power 2x plus c2x multiply e to the power 2x. So from here, you create your y1 and y2. This is from step 2, you have a sub-step 2.1. You identify y1, that is e power 2x, and y2, x e power 2x. So you have y1 and y2. You already found. Now, step 2.2, just a simple step, you create the standard form and then identify your fx. This is already standard form because 1 y double dash minus 4y dash plus 4y. This is your fx. So you already found your fx. It must be in standard form. Otherwise, you cannot use the variation of parameters method. Now, after you find your fx, you want to compute the u1 dash, u2 dash. So the formula says u1 dash w1 divided by w equals to minus y2 fx divided by w. And u2 dash w2 divided by w equals to y1 fx divided by w. So you already knew y1, y2, but w1, w2 not yet. So this is what we want to find. W, w1 and w2. So w is the determinant of matrix 2 by 2 with y1 e power 2x, y2 x e to the power 2x. So first row, according to the formula, you have to go back to the formula. Don't need to change anything. This is your W equals to determinant, first row y1, y2, second row y1 dash, y2 dash. So using that equation, the first row e to x, x e to x, second row, you differentiate. Differentiate e to x, the answer is 2 e to x. Differentiate x e to x, e power 2x, 2x e to x plus product rule, yeah? You differentiate x e to x. Now the determinant of this matrix, e2x multiply 2x e power 2x is 2x e power 4x plus e2x multiply e2x plus e power 4x minus 2x e power 4x. So this one cancel off, remaining term is e power 4x. This is capital W. Small w, W1. W1, first row, 0, Y2. Second row, fx, Y2 dash. So first row, 0, Y2, x e power 2x. Second row, e2x, 1 plus x squared. Y2 dash. Differentiate x e to x using product rule, 2x e to x plus e to x. So 0 multiply 2x e to x plus e to x, 0, minus x multiply e to x e for x divided by 1 plus x squared. So this is your W1. W2, first row y1 0, second row y1 dash fx. Y1 e power 2x 0, y1 dash differentiate e power 2x, 2e 2x, fx e 2x divided by 1 plus x squared. If you take determinant of this matrix, e 2x multiply e 2x, e 4x divided by 1 plus x squared, 2e 2x multiply 0 is 0. So you already have W1, W2. Now you can calculate the U1 dash. U1 dash is W1 divided by W minus x e 4x 1 plus x squared divided by e power 4x. This one cancel off. The answer is minus x 1 plus x squared. U2 dash W2 divided by W. W2 e power 4x 1 plus x squared, W e power 4x. So e power 4x, e power 4x cancel off. So your U1 dash, U2 dash is 1 plus x squared. Now you integrate. So you integrate. When you integrate, you can use all the calculus formulas, but here you no need to put C. And that is the main point here. Because variation parameters, you no need to put C. You just integrate. This one, if you differentiate x squared, 2x. But there is no 2 here. So if you put 2x, then you have to divide by 2. So the answer is minus 1 over 2, ln 1 plus x squared. This is the answer for U1. For U2 dash, 1 over 1 plus x squared, you integrate. You integrate because this is du2 dx. This one comes from the trigonometric formula. Integration of 1 plus 1 or 1 over 1 plus x squared dx is arctangent x. This is well-known formula. Please refer to any calculus book. You will get this answer. So there is no C. Remember, for variation of parameter, for finding U1, U2, no C. So you just have to plug in the U1 minus half ln 1 plus x squared, y1 e power 2x, u2 arctangent x multiplied by x e to x. So you already obtained yp. Take the yp, put it inside your y. That is yc plus yp. Yc is this one. C1 e power 2x plus C2x e power 2x plus yp. You take all and put it here. Minus half ln e power 2x minus half e power 2x ln 1 plus x squared plus x e power 2x arctangent x. So this is the final solution. Any question, class? Any question so far for the example? You can ask any question, general part. If you don't understand any step, you just let me know the slide number and then we will see. Any question so far? Yeah, any questions so far? Any other student? Any other student? Yes, Chow. Okay, thank you. Thank you, Muhammad Ali, Muhammad Amir, Chow. Okay. Farah Shah, how about if the GX have two or more different things? What do you mean by this? I don't understand. If the GX have two or more different things, GX is a function. GX is it can take any form. GX you can refer to previous lecture notes. GX can be ln x, tangent x, sin x, cos x, x power 5, e power x, anything. GX can take any form. So that is the problem. GX. So you have to refer to the forms. GX can take many forms. So that is the problem. So if you understand more example, more exercises, then you will be able to differentiate how to use the variation of parameters or constant coefficient. So end of the day, there will be a confusion which method to use. Either constant coefficient, undetermined coefficient method, or variation of parameters. This is the confusion you will come across at the end of this lecture, because you already finished undetermined coefficient method. So we have to do the final analysis. Which method to use for that particular non-homogeneous part. So for that, there are some guidance already given in the previous lecture. You have to refer to the table. But from here, I already gave you some clue that this function is not easy. E power 2x divided by 1 plus x squared. This one cannot be handled by what we call undetermined coefficient method. Cannot. So that's why we have to use variation of parameter. But the next example, you may think that for this example, look at carefully, example 2, this one is not difficult. You can use undetermined coefficient method. But this part is Euler-Cauchy. So it's not constant coefficient. The whole thing is non-homogeneous Euler-Cauchy. So for this non-homogeneous Cauchy-Euler, you don't use undetermined coefficient method. You use a variation of parameter. This is the best method. Even this function is not very difficult. This function, you may say that we can use undetermined coefficient method because this is only x power 4 ex. But the left-hand side is not constant coefficient. It is Cauchy-Euler. So, but the steps are same. Find the complementary solution. associated homogeneous equation, but this homogeneous equation not constant coefficient because this is Cauchy-Euler. So Cauchy-Euler, x squared y double dash minus 3xy dash plus 3y equals 0. This is am squared plus b minus a m plus c equals 0. So your b is minus 3. A is 1. So minus 3 minus 1 minus 4m plus 3 equals 0. So this is your auxiliary equation. Comes from the Cauchy-Euler. Check, yeah. This is x squared. So x squared y double dash. This is xy dash plus 3y equals 0. This is homogeneous Cauchy-Euler. But there is a non-homogeneous part. So for the homogeneous part, as usual, we try to find auxiliary, but the final solution for the homogeneous, you have to follow the Cauchy-Euler. So you factorize this one 2 times, easy to factorize, m minus 1, m minus equals 0. So m1 equals to 1, m2 equals to 3. So the complementary solution, yc, c1 x to the power m1 plus c2 x to the power m2. So if you simplify yc, c1 x to the power 1 plus c2 x to the power 3. So this is your yc. So from yc, you can create y1, y2. So you create y1x, y2 x power 3. You create. So you already have y1, y2. For the variation of parameter, you must have standard form. How to create standard form? You have to make it 1 y double dash. So this is x squared y double dash. So we cannot use x squared y double dash. So we must make it 1 y double dash. So you have to remove this x squared. That means you divide the whole equation by x squared. So y double dash minus 3x divided by x squared minus 3 over x y dash plus 3 over x squared y, 2x power 4 ex divided by x squared, 2x squared ex. From here, you create your fx. We need our fx. So we already have our fx. We already have y1, y2. Now we can start using variation of parameter. So the important thing is you have to be careful when there is a Cauchy-Euler, then you have to make it standard form. Of course, this is a non-homogeneous ordinary differential equation, but not constant coefficient, but still this is Euler-Cauchy. You can, anytime you can refer back to the previous one. So you already have fx, y1, y2. Now we want to create u1 dash, u2 dash. So you need to find w1, w, w2, w. Of course, you can write w1 minus y2 fx divided by w, u2 dash y1 fx divided by w, or you just write w2 divided by w, w1 divided by w. You must memorize this. So the following is the how you calculate the w. So y1 you already knew, x, y2 x cubed. Yeah. So you already have these both two. So you plug inside here wxx power 3. This is a matrix. Yeah, matrix 2 by 2. First row 1x cubed. Differentiate x1, differentiate x cubed, 3x squared. So find the determinant 3x cubed minus 1x cubed, 2x cubed. So this is your determinant using the algebra 2 by 2 matrix. Now W1, W2, you use the previous formula. First row 0 y2, W1. Second row fx y2 dash. So you have to write the first row only, 0 x cubed But fx, you know already, 2x square x. y2 dash differentiate x cube, 3x square. So determinant 0 multiply 3x square, 0. 0 minus 2x power 5 ex. So this is your W1. So W2, first row y1 0, second row y1 dash fx. So y1 is x, 0 is there, y1 dash differentiate x1 and fx 2x square ex. So determinant x multiply 2x square ex, 2x cube ex minus 1 multiply 0, 0. So this is your W2. So you already have W1, W2. Now you calculate U1 dash. So U1 dash, W1 divided by W minus 2x power 5 ex, 2x cube. These two cancel. X power 5, x power 3, x power 2, e power x. So there is a minus sign. So you have U1 dash minus x squared ex. U2 dash, W2 divided by W, 2x cube ex divided by 2x cube. So this one cancel off. So your U2 dash ex. Now if you want to find U1 and U2, you have to integrate this because this is du1 dx, du2 dx. So you must integrate. So the integration U1 minus x squared ex dx. This one you must use integration by parts. So you refer to integration by part, x squared ex put outside using the formula u dv. Write down here, integration by part u dv. That is the formula u dv equivalent to uv minus v du. So that is the formula how to integrate this. So if you cannot do it now, later on you can do it. So minus x square ex dx, the whole thing, once you simplify, you get minus x square ex plus 2x ex minus 2ex. This is your u1. Take note here we don't need to put c. No. This variation of parameter just to find u1 in terms of x only. So there is no c here. So you no need to put constant c. No need to put constant c. Now u2 is integration of ex dx. This is very easy because single term ex, integrate ex. Only this part because this is x squared. So you must use integration by parts. Now you already have u1, you already have u2. Plug inside this yp, u1x, y1, and then u2x, y2x. So your u1x minus x squared ex plus 2x ex minus 2ex multiplied by your y1x. So your y1x is x. And your u2x is ex. y2x is x cubed. Of course, you can simplify this. How to simplify this? This one x cubed minus x cubed ex plus 2x squared ex. So minus x cubed ex, this one cancel off. This one is 2x squared ex minus 2x ex. So this is your yp. Sometimes can be simplified, but most of the time it will be very hard. So in this case, you can easily simplify. Now you already found yp. Now your y. Y is yc plus yp. So your yc is c1x plus c2x cubed. Your yp is 2x squared ex minus 2x ex. So you can combine these two, you write your y. So if you look at the answer carefully, the constant c1, c2 with yc only. So your yp, there is no constant. So if you have a constant, you just eliminate the constant. You no need to put any constant. Yeah. So this method is different from undetermined coefficients method. So if you are given any problem in the future, you must make your decision whether you want to use undetermined coefficients method or variation of parameters method. And this is the dilemma that you are going to face. So at the moment, we haven't done any analysis yet. Just let us see if you have any problem, then I am ready to give you an idea. Because it is not very sure or guaranteed that for every problem, this variation of parameters will work. Or we cannot say this method is very good method. We never know. So we can try. If you can find the solution, then you can proceed. But if you cannot, then you have to switch to undetermined coefficient method. So let us see if you have any questions, any general questions. Which method is best method, or which method is suitable for any problem? So this slide is slide 26, the last slide. So let us see from you, is there any questions? Any question, class, on variation of parameters? Yes, Muhammad. Ainan. Okay, Aiman. Abdul Hanan. Okay. Muhammad Salihin. Yeah, Dennis. Muhammad Dennis. Any question? Chow. Any question? Chow Jet. Yeah, Natasha. Any questions? Okay, you can write down your questions. No problem. Unfortunately, there is no more examples. For the questions, you have to wait. These notes is not available now. Maybe by end of this week, it will be uploaded. This notes is already uploaded, but you have to refer to the questions, exercises. So exercises, please check in your ULearn. If not uploaded exercises, you just have to wait. So you got to summarize the whole sections. The whole section, include of 5 parts. 2.1, that is a definition and theorem about the homogeneous, non-homogeneous differential equation. For homogeneous constant coefficient, because the right hand side is 0, the gx is 0, so you find auxiliary equations. You find auxiliary equation. So you have, when you solve auxiliary equation, you have 3 roots. There are 3 roots. Real distinct roots. For the second order, differential equation, you will have case 1, two distinct real roots. The word distinct was a technical word. That means you have two different real roots. And case 2 is repeated roots. You must know how to write the YC for repeated roots. That is the problem. The repeated root. You need two independent solutions if it's second order. If it's third order, then you must have three independent solutions. So that's why you put X so that it becomes two independent solutions for the second order. And the third case is complex roots. So you must know how to write the YC for the complex roots. And homogeneous Cauchy-Euler, this is a very special equation. Homogeneous, that means the Gx is 0. So again, you have to have an auxiliary equation and you find three cases. Case 1, distinct real roots. Case 2, repeated roots or equal roots. Case 3, complex roots. Then you form YC. For the non-homogeneous part, we have these two methods. Undetermined coefficient method. Undetermined coefficient method, we already given the table. Please check the table, how you write the YP, the predicted one or the forecast one, the one you guess, smart guess. So once you create the YP from the GX, then you find all the constant. That's why we call it undetermined coefficient method. The constants A, B, C are the undetermined coefficients. Once you found that, then you already completed YP. Then you combine with YC, you get your Y. For the variation of parameter, the difficulty is about the GX. That's why it is different from undetermined coefficient method. If you can use undetermined coefficient method, then you no need to use variation of parameter. You no need to do 2 times. So you have to select which one. If you ask to do both methods, then you try both. But if the question says use undetermined coefficient method, then you cannot use variation of parameters method. So it will be waste of time. So if you ask to use variation of parameters method, then you don't use undetermined coefficient method. Because variation of parameters method is very lengthy. Very lengthy. You go to double check. And then once you find the solution, especially the YP. But the variation of parameter method, the YP depend on the YC. Because you get Y1, Y2 from the homogeneous differential equation. But undetermined coefficient method is different. So you may say the variation of parameter is very lengthy. The method is lengthy. And also it is very tedious. But that is how this method was created. So you got to handle the GX non-homogeneous part with the variation of parameter method. Any question, class, so far? Any questions? Any question, class? Any questions? Okay. Okay, if there is no question, then we move on to the introduction part for chapter 3, which is very difficult, but we will start slowly the first part. So I'm going to change the slide now. Okay. So this one is, the title is Laplace transform for ordinary differential equations. So the keyword here is Laplace transform. So you may ask why we want to study Laplace transform. This is more on philosophical question. I don't want to go into detail for today. Just to give you a very basic idea about Laplace transform. This Laplace transform is, in fact, to solve the linear ordinary differential equations. And that will be in part 3.4 later. So at the moment, we just focused on the basic idea in Laplace transform. I'm not sure whether you studied this before or not, but if you haven't studied, so you have to pay very serious attention, because this is one of the best method to solve linear ordinary differential equation. You already studied chapter 1, the first order, many methods. You studied a linear method, exact, non-exact, Bernoulli, and just we finished second order, homogeneous, non-homogeneous, the method undetermined coefficient, and variation of parameters. But this is the last method that you're going to study. Again, we will solve the same problem. We are solving the problem in chapter 1, linear first order, and also linear second order, by using another method, Laplace transform, which is considered to be one of the most sophisticated method to solve the linear differential equation. Why we are saying this is one of the sophisticated method is yet to be proven by you. You can decide later whether this statement is correct or not through your own experience, because we just cannot make such a statement like that. But you can see later on the flow of the method, how the method is created, designed, or constructed in order to solve successfully the differential equation. Whether second order or the first order, Laplace transform is the one of the best method to solve. So we will deal that the method, the overall method, because we got to study the basic what we call concept, formulas, theorem first. So this we will not go into detail, because for the engineering student, you have to solve many engineering problems. You may ask, what type of engineering problem that you are going to solve? We will show you later in one slide the type of engineering problems. So before we go into the method, we have to define first what is this Laplace transform. For the beginners, you must know a little bit the background of this study. Little bit, yeah. Not very rigorous proof or theorems. Little bit on background, how this Laplace transform was defined and how to make use. So first we have to define and then find Laplace transform for different type of function. Different type means exponent, trigonometric, hyperbolic, polynomial, constant, and so on. So once we already find the Laplace transform, we can create a table. We put it in the table form. This is already done by the scientists. So for the engineers, you just have to make use of the table and then solve your engineering problems. So today we just cover these two parts. Define Laplace transform and then find the Laplace transform. Because you need to know a little bit on the theory. So Laplace transform, the name Laplace comes from this person, Pierre-Simon Laplace, born 1749, and then he lived until 1827. So we want to know what is this Laplace transform, the basic information. This person is, if I'm not mistaken, he is from France, a French mathematician. This is why the Laplace transform was developed or created, because to solve these engineering problems. There are differential equations that will be difficult to solve just by knowing whatever method we have learned so far. So that means the previous method that you studied may not be sufficient enough to solve the differential equation in a very successful way, because there are problems is very difficult to solve with the previous methods. So this is one of the best option you have to solve the differential equation. So many engineers will be wondering where these methods can be applied. What are the applications? One of them is the mass spring system, very famous problem in mechanical engineering. This one is the second order linear constant coefficient non-homogeneous differential equation, because there is Ft. This one involves many variables. M square. M is what we call the mass. D square x dt, dt square. X is the distance variable, t is time variable, plus beta is constant, dx dt, plus k is a constant, maybe this is a spring constant, x is the distance plus ft, function of time. So this is the model. We say the modeling is very important in engineering. So when you model a mass spring system, you can use the idea of differential equation. Of course, you must understand how the system works. And then you create the differential equation based on the engineering system. And then you fix the value m, beta, k, ft, and so on. So that one we can fix from the experts' knowledge, experts' experiences. They can give you the value m, beta, k, ft, and then solving. When we want to solve, of course, we need the method. That's why we emphasize on the method more than the application. Application, definitely you will come across. So there is no doubt about that. We cannot say there is no application on a differential equation. Thousands of applications available. Many fields, not only this mechanical, and in the electrical series of electrical circuit, you have L d square q dt square plus R dq dt plus 1 over cq equals to Et. This is electromagnetic force. L is the inductance, Q is charge, T is time, R is resistance, the C is capacitance. So you have to find the Q. This is the model, the general model. Yeah? We just give you a general idea how the modeling works in engineering, and then the method is available in the differential equations. So, of course, we are not going to solve this immediately now. This is just for information. We already solved the theoretical equation. Of course, you want to know where the theory can be applied in this real-world application. So this is what we call real-world application. But the value of L, R, C, E, T must be given. Otherwise, cannot. This is a general model. Model. Second order, linear, ordinary differential equation, inhomogeneous model. So, of course, the engineers or the experts, they can create the model. Different from this also possible in civil engineering, electrical, mechanical, chemical, computer science, petroleum, geoscience, no problem. So now, this Laplace transform is used to produce an easily solvable algebraic equation from an ordinary differential equation. What is this? This is, you got to wait and see. Later we will show you how this algebraic equation comes into the picture. This Laplace transform involves this solving algebraic equation. So you must be very good in algebra, especially the partial fraction, and then how to make the fraction into decomposition and so on. Of course, the algebra is very important here. And Laplace transform is a typical type of integral transform. So where the Laplace transform comes from? It comes from integral transform. Of course, we cannot go more into detail. In-depth studies not necessary because our main task is here solving the differential equation. So what is the meaning? Meaning we have to spend about 80 to 90% on methods, how to understand and apply the methods. And of course, you want to get the correct output, correct answer. That depends on solely on method. If your method is wrong, then there is no way you can get a correct answer. So that's why you have to study many varieties of methods so that you can have a vast knowledge in different methods, and you can use a different method to verify, validate, test your answers. So this Laplace transform is a special type of integral transform. It has many interesting properties that make it very useful in solving linear IVPs. This is most important part. IVPs stand for initial value problems. Write down, yeah? We already saw this in the beginning of, I think, second chapter about IVPs. This Laplace transform is very suitable to solve linear IVPs, initial value problems, because without the initial value conditions, we cannot apply Laplace transform. This is one of the major issue in Laplace transforms. Applications. Many students ask about application, where this thing can apply. It can be applied in many fields: mathematics, physics, engineering, science, business, finance, economics, and so on. In economics, you want to model. You can use this idea, but you must work with the economists, or the financier, or the business expert, because they will give you the idea how to create the model. Once you have the model, then you can solve the problem. Okay, so we want to look into where the Laplace transform comes from. So as we mentioned before, integral transform. This is the beginning. This is the birth of Laplace transform. Okay, so it comes from integral transform. So integral transform, the definition, yeah, this is definition. So if ft is defined for t greater than 0, and kst is a function of two variables, that is s and t, the improper integral means the upper bound is infinite. And that's why we call it improper integral. So the integration 0 to infinite, kst ft dt equals to limit 0 to b, where b approaches infinity. Kst ft dt is an integral transform. So from here, we want to see how the Laplace transform is developed. So this is the general integral transform. And if you look at this table, very massive, the functions, so many things. So this is table of integral transform. So it includes transform symbol and the k function, and then ft, lower bound t1, t2, and inverse. This one we don't do it now. We do it later. K1, k inverse. And now we concern about the k and ft, t1, t2. This part only. This one only. But this table consists of Fourier transform, Fourier sine, Fourier cosine, Hartley, Mellin, two-sided Laplace transform, Laplace Weierstrass, Henkel, and so on. So we are interested only this one, this Laplace transform. At the moment, this one. Later we will move on to the inverse part. This one later. So you see the symbol here. This is symbol for Laplace. And your k is e power minus omega t, and then your ft is not written here. We will see what is ft, and the lower bound 0, upper bound infinite. So the table of integral transform got so many. So we pick one only, and then we define the Laplace transform. So when the k, capital K, st, this is function of s, distance, is equivalent to e minus e to the power minus st. Very special case. This one is for Laplace transform. So this one you substitute here. So now the capital K disappear. So Laplace transform, you see the L here is a very special symbol. Yeah. So you write like this. L is like this. This L is different. This L, normal L. For Laplace transform, there is a little bit stylish. You can get this symbol in Microsoft Word. So let ft be a function defined t greater than 0 to infinity, and kst is e minus st. Then the integral Laplace of ft 0 to infinite e power minus st ft dt. The ft is the function. It's not given. It's said to be Laplace of ft. Laplace of ft. Ft yet to be known. At the moment, unknown. And provided the integral converges. That means this right-hand side exists. So when you integrate e power minus st ft dt, 0 to infinite, you get the answer. That is the meaning. So the answer for this will be Laplace of ft. So what is ft? That is what you want to explore now. So the ft will be given one by one later on. So you got to wait for a while. We will give you the ft. So first you must familiarize with the notation. The Laplace of ft, this input, the output is fs, capital Fs. That means you are in t domain. This is t domain, yeah? And then this is your s domain. So I put here s. That means you are moving from this planet to this planet, one domain to another domain. So if you take the Laplace of ft, the answer is fs. So the transformation is called Laplace transform. Transformation from one domain, time domain, to distant domain. That's why we call it t to s. So there must be some transformation must take place. What is that? So now we call this particular transformation is called Laplace transform. So what is ft? It's unknown now. So if we give ft, use the definition, find the fs output. But this symbol is capital Fs for small ft, and there is a way how to recognize the notation. For Laplace of small gt, capital Gs. For Laplace of small yt, capital Ys. So the lowercase denote function being transformed, lowercase. And capital letter denote the Laplace transform. Capital F, G, and capital Y. Actually, we are going from T to S at the moment. And the later on, when you study method, you have to come back to T again. That one we call inverse Laplace. Inverse Laplace, L power minus 1. That is from T to S is L. From S to T is inverse Laplace. That one later. So first, we study this first, one by one. Yeah? Simple one first. So what is Laplace of 1? 1 is T power 0. Write down, yeah? This one is T power 0. T power 0 equals to 1. Laplace. So Laplace of ft, when ft is 1. So e power st, ft is 1. So how do integrate? So you can see Laplace of 1, left hand side, the answer is 0 to infinite e minus st multiply 1 dt. So you have to integrate this. So how to integrate this? You look carefully. So you can simplify 1 e power minus st, this one, the integration. So integration of e power minus st dt, you can refer to any calculus book. E minus st dt, e power minus st, differentiate minus st is minus s. So you must divide by minus s, take limit 0 to infinite. Now you want to substitute the limit. So you take out minus 1 over s, integration e power minus st 0 to infinite. Minus 1 over s outside. So this one, e power minus st, better you write 1 over est. Easy to understand when you put the limit. So when your t, s is constant, yeah? When your t is infinite, e power infinite is infinite. 1 over infinite, 0. Minus e power 0. E power 0, 1. 1 over 1, 1. So you simplify this. Minus 1 over s, 0 minus 1. Answer is 1 over s. So that is how you create the Laplace of 1. So now we already have the answer. Laplace of 1, 1 over s. And that becomes a table now. We can create the table. So you can write Laplace of 1, answer is 1 over s. Or Laplace of 1 is t power 0. So 1 over s. 1 over s is capital Fs. Small ft. Ft is 1. Similarly, if you apply the same formula for Laplace of t, Laplace of t, Laplace of ft, this is the general formula. Yeah? 0 to infinite e minus st ft dt. Your ft is t. So Laplace of t 0 to infinite e power minus st tft. If you want to integrate this, the right hand side, you must use integration by parts. uv v du. So e minus st t dt, you can rewrite t e s t dt. This one, integration by part, u dv. You must use the formula u dv. If you know how to use u dv, 0 to infinite e minus st t dt. So your u is t, your dv is e minus st. So uv, so uv t e minus st divided by minus s. Minus integration uv minus v du. uv minus v du. So check your formula. uv, your u is t, your dv is e minus st dt. So the answer is uv minus v. V is minus est divided by minus s. Du is dt. So minus t over s e minus st. This one minus 1 over s e minus st divided by minus s. And then 0 to infinite. So minus t over s e minus st plus 1 over s squared. 1 over infinite, 0 minus e power 0, 1. So the answer is this part 0 to infinite t 0. So this part is cancelled off, first part. So the answer will be 1 over s squared. Minus, minus 1 over s squared. So your Laplace of t, this part is 0 already, 0. And then this part will give you 1 over s squared. So now you can create the table. So this one is for the Laplace of t, 1 over s squared. Laplace of t power 0, you already done 1 over s. So like that you can try for t power 2. And now we try Laplace for e power minus 3t. So use this formula, Laplace of ft, 0 to infinite, e minus st ft dt. So substitute your ft with e power minus 3t. But you can combine these two. That is much more better because easy to integrate. So if you combine these two, e minus st minus 3t, you take out minus 3, you get this function. Now integrate respect to t directly, e minus e power minus s plus 3t divided by minus s plus 3 because this is constant. So 0 to infinite. If you substitute infinite, this becomes 0 minus infinite, 0 minus e power 0, 1. So minus 1 over s plus 3, minus minus, you get 1 plus 1 over s plus 3. So now we already have the table. So Laplace of e power minus 3t, 1 over s plus 3. So what you need is this one. We can collect all these things, put it in the table. So this is what we call the table 1 to 7, the most important table. The rest you can find by using this. These are the basic transform of some functions. So Laplace of 1 is 1 over s. This is special case. And you can generalize Laplace of t power n for n 1, 2, 3, 4, and so on. N factorial divided by s n plus 1. And just now, Laplace of e power minus 3t equals to 1 over s plus 3. But we can generalize Laplace of e power at 1 over s minus 3. If you put a minus 3, this will become s plus 3. We already shown 1, and t power 1, we already shown. If t power 1, 1 factorial 1, s power 2. So we already shown this for n equals to 1. If you don't believe, you can try for n equals to 2. And this one also we already shown. And this one you can show at your free time as an exercise. Laplace of sine kt, k divided by s plus k squared. This is for the trigonometric function. Laplace of cos kt, s divided by s squared plus cos squared. And these two are very special function. This is what we call hyperbolic function. There is a h here, sinh and cos. For Laplace of sinh kt equals to k over s squared plus k squared. You see, different from sin. This is plus. For hyperbolic function, this is minus. For cos hyperbolic, Laplace of cos kt, s over s squared minus k squared. This is plus, this is minus. You can show this an exercise. We already shown for the 1, 2, 3. The rest you can do it at home. So what we need is the final form of Laplace transform. So before we see the example, you see this is the linear combination. Sometimes you have to combine. Laplace of alpha ft plus beta gt is alpha multiplied by Laplace of ft. You take out alpha outside and you take out beta outside. Laplace of gt. So Laplace of ft, the symbol is fs. So alpha fs plus beta gs. Now this example is how you can simplify. Laplace of 1 plus 10t is Laplace of 1 plus 10 times Laplace of t. You no need to repeat the theory. You just write Laplace of 1, 1 over s. Just plug in from the table. And Laplace of t using the previous table, this one, t equals to 1, 1 factorial 1, s power 2. So you already got 1 over s power 2. And you want to simplify this s power 2. This is s plus 10. So final answer is s plus 10 over s squared. So we are now in the s domain. So we already transform the ft 1 plus 10t or ft plus alpha ft plus beta gt, two function combined. This is in st domain. So we transform into s domain. So this is example. Example. Sinh Xing phi t plus t power 4. Okay. Xing Laplace of Xing phi t plus t power 4. You take out a piece of paper. You write down, yeah? You write down. So we want to find Laplace of Xing phi t first. So you write down equals to, write down Laplace of Xing phi t. So you go back to the table, this one, you substitute k with 5. Write down, yeah? K with 5. So you have 5 over s squared minus 25. So you already found. Your answer is 5 over s squared minus 25 plus Laplace of t power 4, t power 4, your n is 4. You go back to the table, n is 4. So 4 factorial divided by s, 4 plus 1. So s power 5. So you plug inside s power 5. So you have 5 over s squared minus 25 plus 24, because 4 factorial is 4 multiplied 3 multiplied by 2 multiplied by 1, 12 multiplied by 2, 24, divided by s power 5. Now if you simplify, 5s power 5 plus 24 s squared minus 25 divided by s power 5 multiplied by s squared minus 25. Or you can simplify 5s power 5 plus 24s power 2 minus 24 multiplied by 25. You calculate, divided by s power 5 in the bracket s squared minus 25. That is the answer. You simplify. You got it, class? You got it? The first one, example 4. From example 1, what happened? Wen Kan. Which one? No. Muhammad Salihin. Which one? Which one? Which one? Example 1. When? Where is example 1? Example 1. From example 1. Laplace of 1. Laplace of ft. 0 to infinite e power minus st ft dt. Can you understand this? Muhammad Salihin, can you understand this? Okay. Now, this ft equals to 1. You substitute 1. So your ft is 1. So est multiply 1 is e power minus st. Integrate this. So you see the following slide. Slowly. You got to exercise. You got to do together. Take piece of paper. Write down. E power minus st dt. The integration. This is integration. So integrate e power st dt. E power st divided by minus s. This is integration. You already studied integration last time. Engineering Maths 1 or calculus. So this one, you take out minus 1 over s in limit e power st from 0 to infinite. But e power minus st, it's better to write 1 over e power st. So minus 1 over s outside, 1 over t is infinite. Why integrate? No, integrate t. Okay, integrate t, not, no, t. Chia Cheng, you misunderstood. S is constant, integrate t, dt. Wong Chen. Yeah, I'm repeating now. Repeat the answer of the Laplace transform. Xing Phi T. Yeah. Chia, you got it wrong. Chia. Integrate respect to C. S, just a constant. Yes. Yes, sir. S is constant. E is variable. So, minus 1 over S outside. 1 over infinite, 0. Minus e power 0, 1. So, minus cancel off, 1 over S. So, Laplace of 1 over S. So, you do it same for Laplace of t, but this one, 2 terms. So, you got to use integration by part. Integration by part. You got to study this class. So, integration by parts. So, this one, you have to do using the formula u dv dt. So, if you use integration formula, you get this answer. Minus t e power minus st divided by s minus e power minus st divided by s squared. So, the t is runs from 0 to infinite. So, this one, even it's infinite, but 1 over infinite, 0. And then the t is 0. So, that's why this one 0. Minus this one is 0 minus 1 over s squared. So, this minus 1 over s squared. Now, Laplace of t become 1 over s squared. This is the formula. So, how to get this? This you do it. You do it exercise. You practice. Yes, S is constant. There you are. So, you are integrating respect to t. This one is your previous exercise. Now, you are studying Laplace class, Laplace transform. Integration, you got to do your homework. So, the answer Laplace t is 1 over s squared. That is the matter. It's not integration. Integration is you have to do. So, once you have that, then it becomes the formula. So, this one, Laplace of t, that's why the table already, we already created the table. This one, Laplace of t, power 1 s squared. But we want to try for Laplace of e power minus 3t. T is the integration respect to t. So, substitute ft, e power minus t, you see here. Slowly, you see here, same. So, this one, e power minus st, e power minus t, minus 3t dt, you have to combine. You combine. This is the trick. You have to combine these together. Now, easy to integrate. You must be very good in integration. Then substitute t. So, this is a minus. So, 1 over infinite, 0 minus 1 over s plus 3. So, 1 plus 1 over s plus 3. This become a formula now. So, we create this table. You need this table. So, now if you don't understand this, it doesn't matter. You need this table. You no need to do this one every time. No. We need this. So if I substitute a minus 3, so 1 over s plus 3. So, correct. But if you substitute a3, then 1 over s minus 3. So for sine, cos, you got to do, you go home and try. Use this formula. Use the formula. Use this formula. Same. ft, substitute ft with sine kt. Substitute ft with cos kt. Substitute ft with sin kt. Substitute ft with cos kt. You try. That is your exercise. So Wang Chen asks, sir, later can you repeat the answer of the Laplace sin phi t plus t power 4? Yes. So that is the exercise. So I want to explain this. Laplace sin phi t plus Laplace of t power 4. Now you see this 5. You go back. Go back. You must refer to this. This one, without this cannot do. So, Laplace of sin kt, k over s squared minus k squared. Write down now. Write down this formula first. So, Laplace of sin kt, k over s squared plus s squared minus k squared. You do it one by one. So, your k is 5. So the answer for Laplace sin phi t is 5 over s squared minus 25. Write down. S squared minus 25. 5 over s squared. 5 over s squared minus 25. That is the answer. Yeah. Can you write down this? This is the answer for Laplace of sin kt. Are you okay, Chia? Wang. Are you okay, Wang? Wang Chen?
Okay, sir. Thank you.
Yeah, you write down. No need to answer.
Right.
Wang. Are you okay? I know, earlier you will be very panicky. No problem. So, Laplace of sin phi t, I know you are not familiar with the sin, but you don't need to worry. This is a hyperbolic function. You have to just match only. Match with this. Don't confuse with sin. This is sin. S-I-N-H. You don't miss this one. This is sine, sinus, cosinus, but this different. So you already have Laplace of sin phi t, 5 over s squared minus 25 plus Laplace of t power 4. Laplace of t power 4, you go back to the table. Your n is 4. You write here. If you don't know, not sure, so your n is 4. Plug in. N is 4. So 4 factorial. Go back to the table again, class. If you don't use table, cannot do. That is not the right way. The right way is Laplace t power n4. Write down 4 factorial. This is factorial. 4 factorial divided by s power 4 plus 1, 5. S power 5. So 4 factorial, you cannot leave like that. You must write. 4 factorial is 24. 24 divided by s power 5. S power 5. Like that. Like this. S power 5. So 5 over s squared minus 25 plus with 24 s power 5. That is the answer. But this one, you have to simplify. The simplify is up to you. You can take the denominator s power 5 multiplied by s squared minus 25. And then the numerator will be 5s power 4 plus 24 in the bracket s squared minus 25. You can leave it like that, or you can simplify it some more. Okay, Wong Chen. Wong, are you okay? Clear? Okay, thank you very much. Okay, good. All right. Now we want to do this. This one, okay. This one, t multiply 2t squared. T multiply 2t, you have to throw away the brackets. T multiply 2t is 2t squared. T multiply 3, 3t. Plus 2 multiply 2, 4t. 3t plus 4t, 7t. Plus 2 multiply 3, 6. So your Laplace will be 2t squared. Write down Laplace of 2t squared plus Laplace of 7t, Laplace of 7t, and Laplace of 6. So Laplace of 2t squared is 2 Laplace of t squared, 2 factorial divided by s power 3, because your n is 2. So the Laplace of 2t squared is 4 over s cubed. And Laplace of 7t, 7 Laplace of t, 1 factorial divided by s squared. So 1 over s squared multiplied by 7, 7 over s squared. Plus Laplace of 6 is 6 Laplace of 1. Laplace of 1 is 1 over s. So 6 multiplied by 1 over s, 6 over s. So the final answer is 4s cubed plus 7s squared plus 6s. So that is the answer for this. So Laplace will be 4 over, if you don't simplify, it's okay. 4 over s cubed, 4 over s cubed, s cubed plus 7 over s squared, s squared plus 6 over s. Can you get this, class? Oh, Muhammad Iskandar got it correct. So Laplace of 2t squared plus Laplace of 7t plus Laplace of 6. You can simplify. But these three things, you can simplify. It's up to you. You can simplify. You can simplify if you want, using the very long factor, s cubed, like this. S cubed, and then you put 4 here, 4 here, plus 7s, and then plus 6s squared. That is just time being to simplify. Long way to go. This is just beginning only. And now the example 6, this is very strange. Example 6, Laplace, evaluate Laplace of ft, whereby ft is minus 1 from 0 to 1, and then ft equals to 1 from t greater than 1 up to infinite. So in this case, you have to see the Laplace formula. Laplace of ft 0 to infinite e power minus st ft dt. But the ft is called piecewise defined function. This got two pieces. So you have to break into two pieces. The first one is 0 to 1 e power minus st multiplied by ft minus 1. Integrate respect to dt. So your answer will be e minus st divided by minus s 0 to 1 plus e power minus st, ft is 1 from limit 1 to infinite. So if you simplify, the first part is minus e power minus st divided by minus s 0 to 1 minus minus positive 1 over s e power minus s. T is 1. T is the variable class. T is the variable. T is 1. And then when t is 0, this is minus 1. So you have 1 over s e power minus s minus 1. Then integration of e power minus st dt e minus st divided by minus s. So minus 1 over s, 0 minus 1, you have 1 over s. So minus 1 over s plus 1 over s, 0. So the final answer will be 1 over 1 over s for this, yeah, final answer 1 over s multiplied by e power minus s. Can you get that, class? That is the answer. For this one, Laplace of ft 1 over s e power minus s. Try this. This is you got to there is no table for this because you are using the formula Laplace of ft 0 to infinite e power minus st ft dt. Now your ft is 0 to 1 minus 1, 1 to infinite, your ft is 1. So you break into two pieces. You break into two pieces. Then you integrate. Finally, you will get this answer. The answer is 1 over s multiplied by e power minus s. Any question, class? So this is the last slide for today. So any questions? Very good. Muhammad Amir, very good. Muhammad Asfa, okay, good. Muhammad Iskandar, okay. Can you get the answer 1 over s e power minus s? For further exercises, please refer to uLearn. Further exercises, you refer to uLearn. This notes is not uploaded yet. You wait until end of this week. End of this week, it will be uploaded. Regarding the quiz, hopefully we will try to make end of this week. So that's all for today. We will stop here. And then see you in the next lecture. Please take your time, you revise. Please take your time. Chapter 3, not yet. Okay, class. We will stop here. See you again. Thank you very much.